In this video, we'll talk about value substitution, which is an easier technique for finding the coefficients needed in a partial fraction decomposition, and then relate all this stuff to doing integrals. Like we saw in the last example, it can be hard to figure out these coefficients when we're doing partial fractions. The setup we had for the last example was the following. And then we reduce this one step further by going to a common denominator on the right, and then setting the numerators equal, which gave us the following expression. And we want an easier way of figuring out a, b, and c from this expression here. I need to know that I have the right number of coefficients before I go forward with this method. So the point is, I had a cubic in the denominator on the left, so my numerator was at most a quadratic because it has to have degree less than the denominator, which has at most 3 coefficients. I have 3 letters, a, b, and c over here, so I'm in good shape. Now I can go to solve this problem. And the point becomes, I need these two things to be equal as polynomials. And since they are both quadratic polynomials, if they're equal at 3 points, they're equal everywhere. So instead of doing this undetermined coefficient stuff where I solve out for the x squared, x, and constant coefficients, what I can do is plug in numbers. And I can plug in 3 numbers into both sides of this equation and allow that to help me solve out for these coefficients. And I want to plug in good numbers that are going to make things a lot simpler. And this idea of plugging in numbers to make it better is called value substitution. So what should I do? Well, if I look at this expression, if I were to plug in 0, what's going to happen? If I plug in 0, the x term over here and the x term over here are both 0, and those two terms go away, which means I'm left with just a and some constants for this problem, and that'll give me the value of a. So we're going to plug in x equals 0. The left-hand side becomes negative 12. The right becomes a times minus 4 times 1 plus 0 plus 0, so minus 4a. And that right there tells me that a is 3. I'm then going to plug in 4. What happens when I plug in 4? Well, the x minus 4 terms both go to 0, and those are just going to be gone now. So let's plug in 4. On the right, I get 2 times 16 is 32, plus 20 is 52, minus 12 is 40, equals 0, plus b times 4 times 5, plus 0, which is 20b, which tells me that b is 2. And then for the last one, I'm going to plug in minus 1 because that'll make the x plus 1 terms go away. And then on the left, I get 2 minus 5 minus 12 is minus 15, is 0 plus 0 plus c times minus 1 times minus 5, which is plus 5c. So then c is minus 3. And I got the exact same numbers that I got last time, but with a much easier way. So the point is, as long as I have the right number of coefficients, and we'll see why that becomes an issue later on, you can just plug in numbers to make your expression look a lot simpler and use that to help you solve the problem. So I'll take this example here. Compute the integral of x squared plus 3 over x plus 1 times x plus 2 times x minus 4, and we'll do this using partial fractions. So partial fraction decomposition, because we have a quadratic on top, which is less than the cubic on the bottom, tells me that I'll be able to write x squared plus 3 over x plus 1, x plus 2, x minus 4 as a over x plus 1 plus b over x plus 2 plus c over x minus 4. And now I want to solve for a, b, and c. So going to a common denominator and then clearing through, or multiplying both sides by this denominator here, gives me the following. X squared plus 3 equals a times x plus 2, x minus 4, because the x plus 1 will cancel with the one that's already there. B x plus 1, x minus 4, c x plus 1, x plus 2. And again, we're going to use value substitution here to solve this problem out. The numbers I'm going to want to plug in are minus 1, minus 2, and 4, because that will get rid of 2 terms each from this expression. So I plug in minus 1, the left-hand side becomes 4. I get a times 1 times minus 5 plus 0 plus 0, which tells me a is minus 4/5. If I plug in minus 2, the left-hand side becomes 7, is 0 plus b times minus 1 times minus 6 plus 0, which gives me that b must be 7 over 6. And then I can plug in x equals 4. If I do that, the left-hand side becomes 19. 0 plus c times 5 times 6, which tells me c is 19 over 30. But now what does this do? This now lets us set up the integral in a way that we can solve it. So then I have the integral x squared plus 3 over x plus 1, x plus 2, x minus 4 dx equals the integral of negative 4/5 over x plus 1 plus 7/6 over x plus 2, 19 over 30 over x minus 4 dx. And now each of these terms I can integrate on their own, right? If I do the whole thing out in detail, I'd write u as being x plus 1 here, get 1 over u, integrate to log of u, plug back in, log of x plus 1. And these will all work the same way for those problems. So what I'll get for the integral is a negative 4/5 log of x plus 1 plus a 7/6 log of x plus 2 plus a 19 over 30 log of x minus 4 plus c. And that's what I get for the antiderivative here. Beforehand, before this section, we would have no way of knowing how to solve this sort of a problem. But now that we have the idea of partial fractions, we can use that method to solve for antiderivatives of any rational function we want, as long as the bottom factors are distinct linear factors. We'll deal with that assumption in the next videos in this section.